Okay, good evening, everyone. My name is Prabhu. I am Secretary of TIFR Alumni Association and currently the Department of Condensed Matter Physics and Material Science at the Kulaba campus of TIFR. It gives me a great pleasure to welcome Mr. Kiran Kumar ji, former chairman of ISRO, the director, TIFR, and all the dignitaries, delegates, friends, and our former colleagues and well-wishers of TIFR for this occasion. Also, I welcome all the alumni members. I wish to take this opportunity to thank all those who helped this happen, which includes all the departments of TIFR responsible for the online arrangements, as well as the arrangements for this event, because it's our customary that we don't give a formal vote of thanks. So I am already thanking them. And now I welcome Professor Jairam Chenglur, Director of TIFR, to initiate this meeting.
Yeah, thank you, Prabhu. I'll be brief. It's my great pleasure to welcome all of you here to today's Aveek Guha Memorial Lecture, which has been organized by the TIFR Alumni Association. And I would like to say again that, TIFR is very fortunate to have such a proactive and engaged alumni association. And they connect to our institute, as you would know, in many, many ways, including by arranging public talks like this, and also by promoting and recognizing excellence, excellence all across the institute, by recognizing faculty and students who have sort of done something extraordinary. And in general, I would say that TAA are really excellent ambassadors of this institute. And I think it's particularly remarkable that they do all of this on a completely voluntary basis. So the TAA started almost 20 years ago, and at that time it had a very modest membership. Now it has a membership of almost 700, more than 700, close to 800 people, and growing very rapidly. And it's also engaged, in a very active enrollment drive, I think, enabled by the graduate school now, also trying to make sure that students, as they graduate, also as a habit, will enroll in the Alumni Association. And I expect the membership to grow very rapidly. And so this is very good news. And we really look forward to working with the Alumni Association across more and more fronts in the years to come. Today's talk is made possible by an endowment by one of our former colleagues, Dr. Guha. Dr. Guha started this lecture series in memory of his son, Aveek, who passed away at a very tragic young age of 43 years. We are fortunate to have with us today a very eminent speaker, the former chairman of ISRO, Kiran Kumar. He will be shortly formally introduced by Prabhu, so I will not do that now. But before I close, I would like to thank TAA for putting this very exciting program together, and Professor Kiran Kumar for very kindly arranging to our request to today's lecture, which we are all looking forward to. Thank you.
Thank you, Professor Chenglur. Now I request our President, TIA Association, to Professor Wahiya, to make his comments.
It's a pleasure to be here, and Dr. Chenglur has already covered broadly the activities of TIA, and it's our pleasure to be working with TIA. We arrange 3 or 4 public lectures every year, plus we have student and faculty appreciation program. We have received a lot of grants from our alumni for specific awards for specific purposes. We do that. We organize lectures, and essentially we try to increase the interaction between TIFR and the alumni of TIFR. But we are also planning to take, Shubha Tole is not here, so I can steal her idea. She has made a series of videos about ex-TIFR members now working in non-TIFR, non-research activities. And we are going to pinch that idea. Huh? Oh, so you heard me. Okay. We are going to sort of enlarge on that idea to give you an idea, to give you a feel that you can do a lot more after doing a PhD in TIFR. And the basic foundation that TIFR gives you still remains a very powerful tool with which to face the world. And it's our pleasure to bring that interaction between faculty, general public, and the alumnus of TIFR. And we thank Dr. Chenglur for his wonderful cooperation and his help that he has been giving us. So with those few words, thank you very much. I would request Prabhuji, we have to give him a gift of thanks, and we have to give him an award, and we have to introduce him.
So thank you, Professor Vahia, for a very nice introduction. Now I have to introduce the speaker. So good evening to all of you, and it's my pleasure and privilege to introduce the speaker, Mr. Kiran Kumar ji. Shri Kiran Kumar ji was born in 1952, graduated in physics from the National College of Bangalore University in 1971, and obtained his MSc Electronics degree in 1973 from the same college. He then moved to IISc Bangalore. From there, he passed his MTech in physical engineering 2 years later in 1975. He started his career with the Space Application Center, Ahmedabad, and eventually went on to become the chairman of the prestigious Indian Space Research Organization, ISRO. And he has made significant contributions to the Indian space program from early days like the Bhaskara TV payload to more recent programs like Chandrayaan-1 and Mangalyaan. He has steered the implementation of the applications-oriented ISRO Indian space program, which has facilitated rapid development of the country in many important spheres of Earth observation, communication, navigation, meteorology, and space science, as well as the development of indigenous launch vehicles and related technologies for providing assured access to space. And he has led design and development of more than 50 electro-optical imaging sensors flown on various spaceborne platforms starting from Bhaskara in 1979. Further, his role in the success of Chandrayaan-1 mission and Mars orbiter mission, he has been very significant, and he has received several awards, some of which are Indian Society of Remote Sensing Award 1984, Individual Service Award by ISRO in 2006, Team Achievement Award of International Academy of Astronautics in 2008, and in 2014 he was awarded Padma Shri, and in 2019 he received France's highest civilian award. So just pardon my French pronunciation, Chevalier de l'Ordre National de la Légion d'Honneur, for his contribution to Indian-France space cooperation. Now, currently, he is the chairman of the Physical Research Development Management Council and is also a member of the Space Commission, Government of India. So now it's my pleasure and honor to invite him to give his lecture.
Beginning. It's in the end, I think. So just to start, we have to go to the beginning. At the outset, thank you very much for giving me this opportunity on the event, Aveek Guha Memorial Lecture. It's indeed very unfortunate that a very capable individual had to see the end of his career at a very early age. But then life, you never know what is in store when it happens. But then his father decided that to keep his memory, it's important that we need to keep engaging with people and telling them about stories of development, stories of success, etc. So as part of this, I have the privilege of talking about Indian space program on this occasion. I should thank Director TIFR and also the TIFR Alumni Association for providing me this opportunity. What I intend to do is take you through the India space program. And in fact, just now I spent a little bit of time outside where, with respect to my own experience, how a lot more is there before the space program started. But anyway, since my career started in Ahmedabad in 1975 with the first Bhaskara satellite activities, my much of interaction with respect to space program was all Sarabhai. And before Sarabhai, of course, there was many things more, which I came to know just now, many things. But then we treat Dr. Sarabhai as the father of the Indian space program. And one of the key things he was telling is, we must be second to none in the application of advanced technologies to the real problems of man and society. And to assure its development, India views science and space technology as a crucial apparatus for its socio-economic development. And Indian space program has been very different and is very deeply rooted to the society. So we are all very familiar that 1957 was when the first object went into the orbit put by Russians. And that in many ways, I think, is a technological capability human beings got in a sort of disruptive technology, which we are all familiar today, how disruptive technologies change the way society lives and goes on. So in 57, when humanity got an ability to go beyond Earth, there were people like Baba and Sarabhai who were looking at India, which was a fledgling democracy, just 10 years into independence, struggling to provide food and shelter, education, looking at how this new capability of going beyond Earth can make a difference to the lives of Indians. So in 1957, the event happened, Sputnik going into orbit. And by 23rd of November 1963, India had already put the first sounding rocket. In fact, just a few days back, the 60th year of celebration was done. And this particular event, how it happened, also pays a great, we need to pay respect to the people at that time. They were able to convince their friends across America, Russia, France, and Germany, and convince them that we have a unique place in India, a geomagnetic equator, where if you conduct upper atmospheric research, it's also beneficial for the scientific community. And with that, we were able to get sounding rockets and then got it assembled in a church and launched it. And at that time, starting with practically no infrastructure, today India is among one of the few countries which has got a capability to put satellites into orbit and also do landing on the moon. So this is what it shows. We have a unique place near Tumba, magnetic equator. And if you do upper atmospheric research there by sending the sounding rockets and collecting information, it is beneficial. And in fact, one of the things that also happened at that time was the church, what you are seeing there is the place near that is where the first sounding rocket was also launched. Dr. Sarabhai had to convince the fishermen in that region that you need to vacate this place and allow us to conduct these experiments. If you do this, one day the country will benefit. In fact, for doing that, he also had to take the services of the priest of the church there. And as though what he had promised was brought into reality, 1999 onwards, you will see in one of the subsequent slides, India was able to provide through an Indian National Information System in Hyderabad, by looking at the color of the ocean and identifying the chlorophyll, and through that, the food chain of the fish, tell the fishermen where in the ocean, if you go, you are assured of a fish catch. So prior to that, of course, what was also done was at that time, why people like Sarabhai, etc., were keen on getting into space was India, if you had to link every part of the country for broadcast, communication, etc., a satellite at geostationary orbit of 36,000 kilometers will provide you 1/3 of the global coverage. And using that, you can link the entire country. And for that, in 1975, India conducted the world's largest socio-technological experiment, an experiment which is, in a way, we are all very familiar today. On our rooftop, you have a 1/4 meter antenna and a set-top box. Through that, you are able to see the television. But way back in the 70s, only the 4 metros had the privilege of seeing that. And at that time, borrowing a satellite from Americans, moving it over to the Indian longitude, and building a system equivalent to today's direct-to-home television. It was called direct-to-community sets. You can see the black and white television sets of ECIL, and then a 10 feet diameter chicken mesh antenna. And what was done is 2,400 villages of our country for 1 year through this broadcasting, information dissemination happened to the villages, and also convincing the government that if you want to reach out to the entire country for both information as well as broadcasting and communication, we need to go the satellite way. Otherwise, the alternative available was you put every 1 kilometer a microwave tower, and then 3.25 million square kilometers of India. You can imagine the number of systems required, cost and effectiveness of that. So by doing this experiment, it was shown to the powers that be that India, if it adopts the space technology, you can quickly progress. And that's how Indian National Satellite System was brought into reality. And here again, one key thing that we need to appreciate is while the key technology itself of the satellite was built by Americans, we were ready to borrow it, use it, and even showcase an application globally, which was very different from what was happening at that time. In fact, this particular activity also received the award, Marconi Award, because it was an example of how technology can be used for societal benefit. Another important thing you can also easily visualize is events like super cyclones used to take away tens of thousands of life in our country. And again, from space, if you are in geostationary orbit, you can look at continuously the Indian landmass and the cloud movement. And through the cloud movement, you can identify when a cyclone forms, and you can also tell ahead of time which portion of the coast the cyclone hits. And today, by virtue of this satellite technology, we are in a position to provide to the disaster relief agency well in advance the information so that they are able to evacuate people there and save the lives. And last many super cyclones have resulted in loss of life less than a single digit, whereas earlier it used to be in tens of thousands. And then again, this shows how progressively with the satellite technology, you are able to identify the track error less than 40 kilometers, and in terms of landfall time, within a half an hour in terms of actual time, and few days in advance, it could be in the range of 3 hours. So by this process, the space technology also brought in significant capability of saving lives through weather monitoring and weather tracking activities. Another thing that happened, of course, was using the space technology for telemedicine and teleeducation. And then telemedicine, when it was much before terrestrial connectivity became what it is today, through the space technology, it was possible to link super specialty hospitals to remote places, Andaman, Nicobar, and then link the patients to the doctors. Those experiments were done. And later, as the terrestrial communication improved, today you are seeing, and also particularly during the COVID time, you have seen how this has taken off in a very significant way. And again, teleeducation, providing remote classrooms through the satellite was a possibility. Now, this was the example what I was trying to tell. This Bishop Peter Bernard Pereira, his services had to be used to convince the fishermen. And then by using satellites and looking at the color of the ocean in 8 different wavelengths, you can identify where exactly is the fish. And to this capability, what we have done recently is we have our own navigation satellites today. And you know that a GPS which can locate itself in terms of latitude, longitude, India came up with only a 7 satellite constellation in comparison with 24 to 32 satellite constellation of Americans, Russians, or Europeans, or even Chinese. And because of that, a small battery operated gadget can be fitted in the boat of the fisherman today. And this gadget locates itself using the NAVIC signals. And not only that, it receives a message from the NAVIC satellites telling about the latitude, longitude of the prospective fishing zone. And then a mobile in the hands of the fisherman. This mobile doesn't have any connectivity to the terrestrial towers, because once you go a few kilometers beyond a tower, no connectivity is possible. But then this mobile communicates with the gadget, and then an app in the mobile tells the fisherman in a video compass mode where he has to go for fishing. Then in his mother tongue, it gives him alerts of weather vagaries that could occur. If the weather is going to be unbearable in the coming days, it alerts him in his mother tongue. Also, many times we have seen in papers, our neighboring countries capture the fishermen because they are wading into their waters. So this gadget also alerts them that you are approaching international boundaries, be careful. But many times they still go because of various reasons, but that apart, the technology is alerting them. So here you can see the example of a person not knowing reading or writing, making the use of the most advanced technology of satellite being put into orbit through launcher, and through that specific information about where he can capture the fish. And with that, in fact, this act alone saves to the country between 10 to 15,000 crores a year. From 99 onwards, you can see what's happening, because the fisherman doesn't have to search for fishing, and also the amount of petrol and diesel he saves amounts to that. That was the kind of estimation that was done some time back. So this is an excellent example of showcasing how even those who are not in a position, who have not had the benefit of reading or writing, can take advantage of the technology when it is brought into use. And then prospective fishing, potential fishing zone, NAVIC services to fishermen. And you will be happy to know that the government has actually now given orders to 3 companies to produce 1 lakh such gadgets, and state governments are going to distribute it to the fishermen. In fact, here also one other thing which I'll touch upon in a later slide, while you can bring in solutions and you can make it technologically feasible to do, but still many things on ground prevent it from happening. In fact, in this case, the government of Tamil Nadu had to be forced by the High Court of Tamil Nadu to tell that you make sure that these gadgets are provided to the fishermen. Otherwise, vested interests were not allowing this to happen. Anyways, once you are in space, you can also collect data in a manner without boundaries. You can look at the entire globe, and then you can collect data over periods of time. And using that, you can make studies about whether it's terrestrial, ocean, atmospheric, cryosphere. And using all that, you can do, there's a national information system for climate and tell is, see, you can bring in these technology solutions, and then the technology solutions, if it has to be adopted and used by the user, first you have to convince him that new approach has to be taken and he can use. It's not always an easy task. I'm sure many of those people who have worked in technology are familiar. If somebody comes and tells us that what we are doing can be done differently or better, first reaction would be, who are you to tell me? I know my job better. So it's always difficult for space technology, as you can visualize, a fledgling democracy getting into various governance activities, a new technology information being provided for usage. Not many departments were willing to adopt and use. So it took different time scales for different departments to start using. Fisheries Survey, Forest Survey of India was one of the early adopters, and even Meteorology Department, they started taking the satellite data, but then processing that data for translating it and bringing it to weather forecasting took another 2 decades later. And then like Airports Authority of India, of course, is providing today GPS-aided augmented navigation system. While Indian subcontinent was a hole in the global network of aircrafts, India is providing that gap since 2003. So in different departments started adopting and started using the use of space technology. And then if you have people at the top who have used it effectively, and if they make up their mind, things move very fast. Was an example, in 2015, we conducted an event where how the space technology can be used in all the governance activities of center and state was brought into actually focus on a 2-day program in Delhi, bringing in all central government and state government secretaries and chiefs of various governance activity. And a 2-day event was conducted. And on that day, Honorable Prime Minister himself spoke extempore 45 minutes, telling the people how space technology can be used in various governance activity. In fact, he had made extensive use of this technology while he was in Gujarat also. So this pushed significantly the way space technology started getting adopted and used. And you will see many examples of how things have moved. Not only did we build our own capabilities, but we also were working with other entities. For example, in megatropics, there was a humidity sounder which provided very useful input for weather monitoring. And similarly in Altica, where we had a cooperation with French government. And then true to our own traditional thing, that the knowledge and skill you acquire should be made available to a bigger community. India decided to provide space-based transponder capability to the neighboring countries, Bangladesh, Bhutan, Maldives, and all that. So using our satellite, what's called as a GSAT-9. And then starting from INSAT, progressively we built the capability of communication. While the first generation of satellites were actually built outside the country, because at that time we did not have the technological capability of doing. But INSAT 2 series onwards, all the satellites are built in the country. And today you have a large number of transponders providing direct-to-home television and also the community connection and Gram Panchayat broadband connectivity. All that is happening. Similarly, this was another thing which I was mentioning. India came up with only a 7-satellite constellation to solve its problem of positioning. And today this is being used very extensively. Already, not only all the aircrafts registered in India beyond 2019 January are expected to carry the satellite-based receivers. There are a large number of ground equipment also which have been realized, including the Fisherman's app, what I was telling. And for doing all this, we had to build the observation capability. We started with Bhaskara way back in 1979, when Russians offered to launch a couple of satellites for us. We built the first remote sensing satellite, starting with 1 kilometer resolution imaging. Progressively, we built, and today we have something like 30 centimeter resolution imaging. The images which can be taken from geostationary platform, that means practically every few minutes you can take some images at coarser resolution, and various capabilities. And also one of the key things is all these capabilities were done with and designed actually done to cater to the specific needs of the country. See, for example, the 3-tier imaging system, what you are seeing here is one of the unique things that was done, where the satellite provides data at very high resolution, medium resolution, and coarse resolution, which is appropriate for the Indian agricultural practices. And similarly, high resolution stereo imaging system was built. And today you can get from 1 kilometer to 0.3 meter, and then few minutes and very high resolution, spatial, spectral, and temporal you can get. In terms of meteorological satellites, again, you may feel many times when you are looking from space, cloud is there in between the Earth and the satellite, particularly during the monsoon months, June to September. What use will the satellite data be? But then, like visible and infrared is transparent through the glass. Cloud is transparent for microwave. So we build microwave sensors and radars for generating data during that period and provide. In fact, today we also provide significant amount of data from our microwave satellites to the global weather forecasting community within 180 minutes of acquiring the data of any region, ocean wind vector, or vertical and horizontal temperature and humidity profiles. And hyperspectral imaging is again like making observation in very many wavelengths, almost up to 250 odd wavelengths. You can get very different information about the crop type, crop vigor, and crop infestation, etc. This is the microwave technology I was talking about. See, starting with Bhaskara time, a microwave radiometer. Today we have a number of C-band and X-band synthetic aperture radar, which provides very highly repetitive data for the Indian region and also global connectivity. While we were doing all this, we were also making sure that space science activity, which is one of the essential things for you to build capability and modify that capability for various other applications, right from Aryabhatta onwards, experiments were being done, scientific experiments. X-ray astronomy, aeronomy, and solar physics was the first one on Aryabhatta. Then I'm sure in TIFR also there are a lot of activity related to Space Lab Anuradha, and then SROS. And each of the opportunity that was there, space science experiments were being done. And Chandrayaan-1, when it was done in 2008, again, it was a significant change in the approach, because as you keep building your capability in the technology of launch vehicles, satellite, and applications, unless you challenge the people working with greater and greater or more difficult problems, you cannot improve their skill set, or you cannot go beyond where they stand today. So with missions like Chandrayaan, Mars Orbiter, Astrosat, etc., all fall into that category. In fact, while man had already landed on the moon and a large number of probes had touched the surface of the moon, Chandrayaan-1 gets the credit for discovering the presence of the water. And that again shows it is never too late to achieve or discover and find new things. And beyond Chandrayaan-1, of course, we'll touch upon it a little more later. Chandrayaan-2 and Chandrayaan-3, where we have done the soft landing, work was done. And Mars Orbiter mission, again, if you see, it was a very unique thing where you could go almost like travel 600 million kilometers. And just if you want to appreciate the kind of problem that was there in that, on the 5th of November 2013, the satellite, when it was launched from Shri, task cutout was travel a distance of about 600 million kilometers over 10 months. And at the end of the period, on 2014, September 24th, morning 7:30 a.m., to that second, you imagine a 50-kilometer cube in space. This satellite had to be inside that on that day and that second. If it were not there, it would not have been possible to do the required reorientation and get captured by that. And what kind of forces could have deviated that satellite, if you imagine? Even sunlight falling on the satellite can produce enough force, radiation pressure, to deviate it from its trajectory. So not only you need to know its trajectory accurately, but also you have to compensate for all that and then make the thing work. So in terms of the lunar mission itself, Chandrayaan-1 carried a uncontrolled descent moon impact probe, which touched a place near Shackleton crater. And it also carried a mass spectrometer, which did detect some OH and water molecules on its way. But then you are all very familiar. If you want to prove something, what you have observed, you need a lot of corroborative information. And that's how, for example, the other instrument that was carried on Chandrayaan-1, which was actually built by the American friends, NASA and APL, etc., which was carrying moon mineralogy mapper and synthetic aperture radar. Using that was demonstrated. And in Chandrayaan-2, 2019, when we did this, all the instruments were indigenously built. The spectrometer, which was operating up to 3 microns, was moved up to 5 micron. And then instead of a single frequency synthetic aperture radar, we used dual frequency synthetic aperture radar. And over the 4 years period before Chandrayaan-3, we could collect a lot of information, which helped us do our Chandrayaan-3 activity very successfully. And then these are some of the results of Chandrayaan-2, where argon mapping is done and dual frequency synthetic aperture radar is able to identify even some of the things hidden below the surface. And one of the images, what you are seeing here, this particular image, is among the orbiters on moon, this camera produces the highest resolution imaging. In fact, it is on the backbone of this image that you can say we were able to successfully touch down in Chandrayaan-3. I'll touch upon that topic in a subsequent slide. And then you can generate various information about the lunar surface. And today we have the entire lunar surface mapped in the various wavelength region. And Mars orbiter mission, again, it was originally planned for about a 6 months activity. Within the limited constraints of the launch vehicle you have and the fuel you can carry in that launch vehicle, this mission was conceived and it was achieved. And then AstroSat mission, again, very unique in many sense, because ISRO was able to actually provide the requisite support for many academic institutions, including TIFR, where the instrument that was carried on this AstroSat provided virgin data to the Indian researchers. And also in a particular wavelength in far ultraviolet region, this carries a telescope which has the highest angular resolution and sensitivity, better than any other instrument in the world today. So as a result of that, large number of studies and research work is going on in the country. So for doing all this activity, obviously you needed to build a capability of launch vehicle. So starting with a simple, the sounding rockets, by now we have done more than 223 missions, which includes about 59 PSLVs, and Polar Satellite Launch Vehicle is considered as one of the very credible vehicles. Then GSLV, Geostationary Launch Vehicle, which makes use of the cryogenic engines. And then apart from our own satellites, we have also launched about 430 satellites of other countries. And for doing that, like way back in '94 was the first PSLV. And with each launch, its capability was being increased. And it was also one of the first launcher to be used for putting a satellite into geostationary transfer orbit without cryo engine. And then it was the first launcher to put our moon mission, Mars mission. And we have demonstrated using this launch vehicle that you can put multiple satellites into orbit and satellites into multiple orbits. All that has been done using this. And then similarly, in terms of GSLV, if you see, while the first few launch vehicles were done with the support from USSR for technology transfer based agreement, but then geopolitical situation did not allow this to go on. And then in a way, it was a blessing in disguise. Today, India has its own version of cryogenic engine, and we are moving ahead using that for both the manned version also. In fact, much of these facilities had to be established to make sure that your cryogenic engine works satisfactorily. A large number of test facilities was required to be done. And using these particular activities, this just lists some of the things that were done during that period. And then bringing together for national development is one of the key activities. While the government entity like ISRO itself, it can do certain amount of work, but then as the country progresses, you need a large collaborative effort. Before that, I'll just touch upon some of the things that were also done. See, we had this semiconductors laboratory at Chandigarh. For a certain period of time, it was under the custody of Department of Space. So during that time, not only we built 180 nanometer technology devices were realized using that, we built a processor chip which is used for our launch vehicles computer, and also for the synthetic aperture radar processor chips were developed here. CCD charge coupled devices, which we have flown on many satellites, and also our latest OceanSat, which carries the information that is required, like what I was telling for the prospective fishing zone. This detector used in that has come out of this place. And then obviously you also need a large amount of computational capability and various softwares that are required. Feast, for example, is a finite element analysis software, which is now made available in the country through the enterprise. There are 3 versions of which it is available, and every year that is getting augmented with new additions. And then for this activity, a large number of industry had to be supported for doing new work. And this just gives you miraging steel when it was not available, how it was done. And then building hypersonic and wind tunnel test facilities for doing various validation of the new designs and concepts. This is done. Then again, similarly, in terms of propellant and chemicals, in fact, one of the chemical factory at Bombay in Rasayani had to be taken over by us and run, because otherwise it would have prevented launches from happening. So in the similar way, you can see Midani, not only for titanium and many other material, titanium sponge and copper alloy, aluminum. And in addition to that, the lithium ion battery, which we use not only for our launch vehicle, but also for the satellite. This technology also was transferred to a number of companies in India. This again is a few examples of the kind of thing that are done. Okay, so one of the things that I just want to bring to your notice is Sarabhai's vision of enabling India was to leapfrog into the future through the adoption of appropriate technologies. In fact, in SITE, when the first experiment was done, the adoption was done in such a way that we came up with a three-in-one configuration for INSAT. At that point of time in the 80s, single satellite providing broadcasting, communication, and meteorology was not existing. And we adopted that both because we could not afford multiple launches and multiple satellites. All 3 were combined in one. And then between 95 and 99, in the civilian domain, India was providing the highest resolution imaging globally. More than 18 ground stations across the globe were receiving that. And by 1999, Iconos came up with 1 meter imaging, and that's how the things changed. While in military domain, much better resolution was there, India was able to do this again by adopting technology. There was a concept of a very compact telescope, which was there in the literature, but nobody had attempted to realize that, because at the time it was conceived, technological complexity and capability of doing 5-axis polishing machines or interferometric testing did not exist. But when we were trying to do, we realized that the enabling technologies were available. So we became the first country or first space agency to adopt this kind of telescope, and we were able to go ahead. Similarly, Mars orbiter mission, you saw that we were the first in a maiden attempt to reach the Mars orbit. And then AstroSat, I already talked about, one of the in a particular wavelength region, you have the highest angular resolution. And similarly, when the 104 satellites was put in one go, it became sort of a record. But at that time, that was not done for the record, but it was only to make use of the excess capacity that is available in our launcher. After putting our primary satellite, you still had so much of space that you could put these satellites. And also at that point, this was a requirement, because as miniaturization keeps happening, what could be done earlier with huge ton weighing satellites or meters volume, miniature satellites started coming into picture. And then there were not many people taking such satellites into orbit. So all this showed, this is just, of course, an indication of what the leapfrogging itself is about. When you want to do a high jump, if you have the space for doing the running, you can do the enough momentum creation and then jump. But if you do not have that kind of a resource, what do? That's what leapfrogging was all about, and what Dr. Sarabhai and people like him were talking about at that time. Then subsequently, of course, Gaganyaan. Originally, India had a plan of doing the Indian astronaut getting into orbit before the 75th year of independence. But then COVID delayed the whole thing. But a lot of work is going on this. And recently, we also had one of the recovery experiments done. And man rating, one of the things we need to appreciate is the launch vehicle, whatever was used earlier. If you have to use it for carrying humans, then you have to make sure that they are human rated. And if it has to be human rated, then there's a host of other activities which you have to make sure. And for doing that, these activities are all important, and it's going on in that. And then Aditya L1 again, this is on the way. By January 2nd week, we should be in the right place where we can get into the halo orbit. And this is also going to provide some unique capabilities for the researchers to carry out experiments on coronal studies, hard X-rays, UV imaging, etc. And another important aspect we also need to appreciate is people recognize you for your demonstrated capability and not claimed capability. In fact, this particular mission is in many ways an example of that. So while we had borrowed from Americans a satellite, and later with our the nuclear experiments, etc., we came under ban, and then things were, in terms of cooperation, nothing much was happening. But then after our Chandrayaan-1 launch and our own synthetic aperture radar missions, we are working for almost a decade now, and the launch will take place early next year. This is a synthetic aperture radar, which is one of the very advanced technology satellites, which has got L-band and S-band synthetic aperture radar in a sweep-SAR mode. The prime payload itself is being built at America. The S-band component of that we are doing. The payload is put on a satellite, our satellite, and we will be launching it. And this will provide information globally at a rate where you can generate 3D changes or three-dimensional changes to the tune of few centimeters of the entire globe. So a huge opportunity this is going to provide. And they were ready to work with us once you demonstrated both Chandrayaan-1 and SAR. And then today, a few experiments that have happened is this is a crew module which has been actually brought back after the launch. Just last month only this activity happened. And ISRO worked with a large number of other entities in the country. And you can see how this particular capsule was recovered and moved. And this was one part of the human space program activity. Maybe I'll just spend a couple of minutes on Chandrayaan-3 itself, because that's a current topic of interest, and what happened between 2019 and 2023 helped us do the thing. See, when we did the activity in 2019, one of the key things you need to visualize is the place where you are going to land. You need to know that place very well, because where you are putting all the four legs of the lander, it should not enter into a crater. It should not sit on a boulder. That means, and also when it lands, it should not be on an inclined surface, so it topples, etc. So you need to know of that place very accurately. But then at that point of time, whatever data was accessible to that, by making use of that, we had chosen an area which you can say is roughly about, okay. Here, if you see the landing site was an area of 500 meter by 500 meter with the knowledge that we had at that time. But by now, what we did with the satellite data, what I showed, 25 centimeter data, for this entire 750 kilometer strip, we could collect data using our own payload and then generated an area where we want to land. That size was 4 kilometers by 2 kilometers. Not only that, within that, any 150 meter diameter you take, you can touch down in that 150 meter safely with the 4 legs. So that was the kind of place that was identified. So because of that, you can imagine starting somewhere, doing all the activities up to that point. Now you have a wider error margin. So you can, even if you are reaching that place with a larger error, and when you are hovering at that point, you take an image of the current region, compare it with the data already stored in the system, and by making use of that, whether you need to move laterally, you can determine. So all that preparation had been done here. So one of the thing was the landing site was made much larger, so error margin had been increased. Second thing was, again, starting point. Again, you can visualize if you want to do a particular job and you want to go and touch down somewhere, you need to know your current position, velocity, direction very accurately. And then if you know that, then all the things you are planning in terms of operation can be successfully done. So during these 4 years, our ability to track and monitor the orbit and then determine its position was also increased tremendously. And we were in a position to determine the orbital positions very accurately. That was the second development that happened. And then if you look at, So another thing that was there is, see, this particular satellite, means the image you are quite familiar, because of our launcher is not in a position to inject the satellite directly with the requisite velocity to go to moon. What we were doing is, each time the satellite is in an elliptical orbit, whenever it comes to perigee, using the engines on the satellite, you add a small velocity to it, and then that way you progressively increase the capacity, the velocity, and then finally move towards moon and get acquired. There you do exactly the reverse. Because you have a minimal capacity, you get into a highly elliptical orbit, then progressively you keep reducing it and achieve the requisite orbit. And then once you are in the actual 100-kilometer orbit, the requirement is you have to separate the lander from the orbiter or the propulsion module, and then all operations have to be done by the lander itself. So the engines that are required to be put on the lander, this was again a new development, because as you can see, when you are in an orbiting space, if you reduce all your horizontal velocity becomes 0, the object will fall freely vertical. So if you want to prevent that, you have to compensate the gravity by providing the opposite thrust. But if you do it with exactly, it will remain there stationary. So you are trying to bring it down and make it touch softly. So it means the compensation you are doing, you should be able to do in a controlled manner, change it. That means throttling capability is required. So in Chandrayaan-2, we were building our launch vehicle, means the engines, with a throttling capability. Up to that point in time, all the engines we had been building were, once you start the process of firing, they will provide a fixed thrust till the fuel is exhausted. Whereas here, we had to build a mechanism where you could change it in a controlled manner. And again, to start with, you have to compensate a lot. As you keep coming down, you are exhausting the fuel, the weight is coming down, and then your same capacity is inadequate. So throttling becomes very much deep, etc. So to address all that, that kind of an engine had to be built. And when they are operating, in terms of your expectation and your ground evaluation, you have certain limits of performance. And if they go beyond those limits of performance, then your ability to deal with such a situation becomes an issue. So that also could be addressed by incorporating, in this case, the trials that were done from taking from 100 by 100 to 100 by 30, we made use of the same engines which are there on the lander and exercise that capacity to change this behavior. So you could exactly verify all the engines, what you have put, whether they are doing their function, whether they are actually throttling the way you are expecting. In case there are changes in that, you could incorporate your model appropriately and change. So we had built a provision to test it in orbit. So these were the things which really helped in achieving this particular case. Apart from that, of course, a number of inertial sensors are there. Inertial sensors allow you to know your current position, and then based on the velocity change, then you can determine how far you have traveled, what direction you have traveled. But then inertial sensors are alone not sufficient. You need to make use of absolute sensors and verify. So that's how when you reach something like at the end of rough braking phase, you have got a horizontal velocity of around 60 meters, 350 meters, and vertical velocity 60 meters. That time you make use of altimeter and determine the height. And if your height is beyond certain limits, then you change the trajectory of coming down. So then you come down to a vertical hovering, take the image, match the image, and then progressively come down. So in this way, because now you had more fuel we carried this time, and all the systems were tested on ground, integrated way, and you built algorithms. Once you have more resources available, the robustness of the algorithms that you can bring also is that much more. So all these things helped us in achieving what was required to be done. Okay. So in a way, you can see a lot of activity happens behind the scenes for ensuring that you succeed. And then the preparation that had gone on was one of the key things, and also improved knowledge and addressing the failures, what you encountered, and how you could minimize that, and how you could build more robustness. So the robustness improvement, of course, itself, like I pointed out, was one in terms of the fuel. We were able to carry more fuel. So you have more fuel available. In fact, it so happened that after we touched down, we still had enough fuel. So we did an experiment of hopping. That means from wherever you are, you just jumped up and then came back down again. And in fact, that gave one very interesting result also. I was just mentioning to Director that these X-band spectrum that we were getting, the moment it touches the surface, it got distorted. And then when it took off again, it was becoming normal. So a lot of such interesting things are there that is happening. And of course, the lander rover came out and we could do the experiment for one lunar day. And of course, we had to shut down little early. Why? Many people, if we find out, it's odd. We actually lost 4 days of the lunar day, because first 2 days we could not have used. When the sun is coming above the horizon, the solar panel should get the power if it is to generate power. So if it is at the very low elevation, long shadows of any object could prevent panel from receiving sunlight. So we have to wait for certain elevation. So first 2 days later only we entered into the landing. Same way we had to shut down little early, because when the sun is again setting, we don't want the shadow to cause the problem. And in case it comes back after one lunar night, we should be ready. So we have to reorient the lander and keep it ready for horizon, sun coming up on the horizon. But anyway, we could not survive one lunar night simply because systems are not designed for that long duration, low temperature excursion. If you were to do that, you would require either nuclear powered RTGs, or you require other components to be designed in such a way that they can withstand that extreme conditions, which would have again increase the cost of the system. So then Chandrayaan-3, what it again demonstrated is that it is possible for you to learn from your previous mistakes, and then if you address them appropriately, you can build a capability of overcoming them. And in fact, on this particular event itself made a huge impact globally. Apart from that, today, if you see in terms of the way things are, while ISRO worked for last 5.5 decades and brought it to a certain level, the globe has moved on. World is not stationary. Unlike in the earlier time, it is no longer the nation states which are doing space activity. It is a lot of private companies have got into space activity. And today, they are moving ahead at such a pace, like man conquered land, ocean, airspace. Now he's trying to look at how can he dominate airspace itself or space itself. So now space, you're talking about space for tourism, space for habitation, space for exploitation, you name it. And then India also looking at space economy, which is supposed to be a few $1 trillion in the coming years. Should it be prevented from taking advantages of the technological capability it has built? So the government is trying to move beyond only the government agencies doing work in space. It has provided enabling condition for in the entire country by changing its policy law. And then there are more and more private startups which have come up. And then government has also announced by 2040, we will have an Indian landing on the moon. And by 2035, we will have a space station of our own. So all these activities are going on. And in this, we need to really appreciate that if you are capable of looking at what technology tool is available to you and how you can use it for solving the problems you are facing, you can definitely do things which others will take note of. And if whatever has happened, whether it in this particular case of complete space technology travel, it is a demonstration of that. I'll just end my talk with just a couple of interesting quotes from Dr. Sarabhai. So one of the things he said is, an important ingredient for satisfactory meeting the challenge of the changing environment is not experience, but an ability to learn. It is said when he was given the task of actually recruiting people for Atira in Ahmedabad, his advertisement carried a statement, those with experience need not apply. The idea is, if you are already having certain experience, maybe you are already thinking in a particular direction. Your thought processes are limited. You are not open to the problem fully. So that was one of the points. But then anyway, it's a perspective we need to keep in mind. Experience is less relevant than knowledge. More than that, the ability to learn and innovate. Today, all the new education policy or the problems of students, etc., is only this. How do we learn the process of learning rather than the content of learning? And then finally, technology is not an objective to be aimed at, but a tool to be used for the benefit of common man or humanity in general. Today, what we are seeing in general is technology is moving inexorably towards excellence in all directions, no matter who is doing, whether it's from a doctor or a mechanical engineer, you name any area. Human being is trying to and mimic nature and create things what he is seeing in nature. But then in our desire to make things happen rapidly, many times we are upsetting the balance of the things around us. So sustainable development becomes important. And if sustainability is an essential thing, we need to understand that life on Earth, if it has to be continuing, human being needs to appreciate that he is not the sole occupant of this universe or the planet. He needs to actually respect nature and also other life forms. Then only things can happen. That is the true, you can say, message of this land. And that's how India is making a difference in many of the things it is doing. Maybe I'll stop here, and if you have any questions, I'll be more than happy to answer.